I'm here today to talk about something a little different to my usual day job actually. So whereas I'm a full stack software engineer usually building business scale applications, I'm actually here to present something I've been working on in my own time as a means of learning something a little bit different and broadening my skill set really. So to introduce who I actually am, my name's James. I'm a software engineer who's been at it commercially for over 11 years now. Mostly work with JavaScript and Golang, although for the most part, if it's not Java, I'm always open to it. I've delivered multiple technical projects throughout my career in various industries, so e-commerce, media. I was recently at a cloud data company doing really cool integrations with Databricks, Snowflake, and I was building the billing systems behind that. So really cool mixture of products and technologies. And I'm currently employed, well, it's my third week actually, at a company called Hollybob, which is a SaaS platform for travel companies to resell their travel experiences to other businesses, so suppliers of holidays, tourism packages, etc. But I'm not particularly here to talk about that, as I mentioned. So this talk, because I imagine there's probably a mix of experience levels, I'm going to introduce what containerisation is, set the backdrop, and then I'm going to lead into the subject proposed by the actual title slide. So, and at any point, I know there's a lot of discussion at these meetups and questions, so if any questions arise at any point, then please just holler and feel free to interject at any time. So, in terms of software deployment, scaling and clustering, which I think sets the backdrop really nicely for the content of this talk. So, for many years, there have been myriad ways to deploy software applications, back-end software services particularly. So FTP scripts directly to the production server, so uploading PHP files to a server with PHP installed. Common Gateway Interface or CGI bin, which I think I poked around with once when I was about 13, so not something I really had to use commercially. And probably prior to containerisation, the approach I used the most was packaging services as virtual machine images and placing them onto some server somewhere with a hypervisor running. And deploying these deterministic, that is to say they build in the exact same way every time, and portable software artifacts so they run the same way everywhere, it's always been challenging historically. And then also scaling these services, so once you've overcome the challenges of deployment, actually making the application suitable and scalable to differing demands, different traffic at different periods. So there's horizontal scaling, typically, where you have a cluster of nodes, hardware nodes that serve a particular application or set of applications. And horizontal scaling involves adding new nodes to an existing cluster in order to add capacity and removing them when the capacity winds down. And then there's also vertical scaling, which is to take the existing hardware and increase the capacity by increasing the hardware of the individual nodes, so increasing the processor, increasing the RAM. And in my experience, which is quite limited to more typical commercial applications admittedly, I found that the industry over time has shifted towards horizontal scaling, but I'm sure there are particular use cases where you might want to consider vertical. And with like AWS and cloud platforms, it's essentially going more horizontal. And clustering solutions have been available for multiple decades. So I entered the industry in 2012, so a lot of this is more historical for me. In my research, I came across Linux HA, which was a means of clustering Linux servers, and then you could run your own application servers on the individual boxes. And that was back in 1999 when I hadn't even written my first line of code. And up until today, when really Kubernetes is the prevalent clustering solution, and that ties in quite nicely with containerisation as well. So what actually is containerisation? Fundamentally, it's a virtualization primitive. and it provides a means of packaging software along with any required dependencies into a self-contained image. And so an image is essentially a pre-built application or a set of dependencies from which you can derive your own images. And you can create instances of these images called containers. So you could build an application server, build an image of that server, and then you could have multiple containers of that application server that you can create at will and deploy accordingly. So in contrast to virtual machines, which will contain the full operating system in each image, containers run on top of an execution engine typically. And instead of having a guest OS in the virtual machine, for containers, the execution engine will interact with the host operating system's kernel directly for any I/O and system resource type pieces. And more concretely, in Docker, which we'll go into, these make use of Linux namespaces and C groups to isolate the Docker container processes from every other system process. So it's actually a lot more lightweight than virtual machines, and it makes use of existing primitives in Linux. And they can be efficiently rebuilt and updated in remote registries. So they're layered, which I'll go into more deeply subsequently. So in the procedural build stage for a container, that step is essentially hashed. So if a change isn't detected, i.e. if the computed hash for that layer is the same between builds, Docker won't, or the container engine of your choice, won't rebuild that layer. And then when you publish, if the hash is the same, it won't publish those redundant megabytes. So rather than having to push the entire thing on rebuild, it will only rebuild and push the layers that have actually changed in the first place. And the learnings of the past 50 years, starting with Linux's CH root, so I think my parents were probably in their infancy when that was a thing, which allowed for that sort of operating system / kernel level isolation I mentioned. That really paved the way. A lot of those learnings ultimately led to Docker being released in 2013. And that was essentially retrofitted into a set of specifications called the Open Container Initiative a couple of years later. And since then, I wouldn't say alternative container technologies have flooded the industry, but many more have emerged. So there are some that are OCI compliant, like Podman and runC. So you can take containers built with Docker, Podman and runC and throw them at any OCI compliant execution engine and they should work. And then there's also others that have taken a completely different path, such as Linux containers. But this talk will predominantly focus on Docker. So creating and running a container using Docker. You can use a myriad of commands to run containers, but the most straightforward one is docker run and then the image name. You can provide a tag, you can provide arguments to the container, but I won't go into that too deeply right now. So here we're running the hello world container, and what this will do, it will look for the image locally. You can see it's not found. So it will pull from Docker's default registry by default. You can have alternative registries that you point to, but by default it will pull from Docker's remote and self-managed registry. So it pulls that image, it executes the default command for that container, and it literally just prints a message. So and that's essentially a portable isolated image with, albeit a very simple example. So there are two predominant ways, at least I would consider, that allow you to create an image. So the first is Docker files. So typically it's a set of instructions. So I mentioned the layers previously. So each of these steps, or I think most of the steps here, will create an individual layer that can be cached and rehashed and then rebuilt accordingly. So the from argument lets me choose a base image. So dnote is a JavaScript runtime similar to Node. They provide base images. So I'm deriving from that base image. I have some arguments for my application that you can pass in at, I believe, can't remember, I think they're build time arguments, essentially. So when you're building the image, you provide these arguments and they get injected in. You can copy directory, set the working directory for the application. I'm specifying a user that the application should run as within the container, setting some runtime environment variables based on the build args, and then doing a specific build step. Now, this expose command doesn't actually expose the port automatically, by the way, as an aside. It's just essentially a directive that tells you, it's essentially documentation to say you should expose port 8080 because this application is going to be available on port 8080 within the container itself. And then the command. So the default command or entry point is Dino. So here the command, this list will be appended to that entry point, I believe. So that actually runs the application. So you can build that accordingly with the docker build command. We give it a tag that gives it a nice name, and this colon is essentially a modifier to that tag name, so you can version it accordingly, or you don't have to put a version number, it can be any string of characters. And then dot means the current working directory, which means Docker will find a Docker, it will look for a Docker file in the working directory and then build that accordingly. The second way, which is what I've been experimenting with recently, are build packs. So rather than you having to provide a Docker file, you can use a build pack. So this is Paketo specifically, if I recall correctly, where you give it a set of builders for your services. And based on what it can infer from your application and these builders you provide, it will build an OCI compliant image for you, and you don't have to author your Docker files necessarily. So for example, a Java one, we use the Jammy Full base, which I believe is based on Ubuntu if I recall correctly, and then specific build packs for Java and Spring Boot, and then for the Python package we have a Python build pack. So this was just some example that I put together for another talk a few months ago. So you have a builder fundamentally, and then you have the build packs you can compose on top to create OCI compliant containers for your software.
Quick question.
Yeah.
That builder, sorry. Is that like a skeleton boilerplate basically that you're running there? That builder jamming full?
Yes, so I'll just switch to GitHub. No, it's okay. So if I look for builder, is it builder jammy base? Builder jammy full. I think I needed the full one in both instances for some reason, but I can't remember why. So Paketo will provide the build packs and the builder bases. So yeah, it's essentially a configuration and a set of scripts that will bring that base operating system or that base image on which the output image is derived. So you're not having to write all the boilerplate code yourself. Yeah. It's more a configuration of the correct build pack and the builders in order to build your specific application. Yeah. And a lot of what it tries to build, from what I understand, is inferred as well. Yeah. But then you're compared to, so it's more, it just generates the container based upon the build pack and the builders. So you're not even having to write any particular boilerplate to support that. It just essentially builds the image based on the packs and the builder that you provide to it. Okay. So it's a lot more, it takes a bit of trial and error, I found, but it's a lot less verbose than having to manage Docker files. I think I'm probably starting to prefer this, but it depends what I'm trying to achieve at the end of the day.
It sets some standards, doesn't it, as well?
Yeah.
In some respects, so you're not having to like rethink about standards every time you're doing all this stuff.
Yeah, exactly. And if you're authoring Docker files, yeah, precisely. If you're authoring Docker files within your organisation, then having to set standards or find an existing standard, it's still time consumed and effort, and I think this can essentially save a lot of those headaches and a lot of that effort.
Thank you for that.
You're all right. So publishing images, so you can use in Docker the docker push command with the image tag. Now by default this will push to the Docker registry, but there's a plethora of registries, so Amazon ECR for example, and you can push to that and it integrates with Amazon ECS, which we'll get into, or you could self-manage your own registry for example. And deployment targets for these containerization technologies, so you could run Docker or Podman, which is also OCI compliant, on your own infrastructure. Could be an EC2 instance directly. There's Amazon ECS, which runs containers directly. Fargate, where it sits on top of ECS and you don't have to manage the capacity. It's essentially serverless containers where it will essentially scale based on capacity for you. And interestingly, it can target Amazon Elastic Kubernetes service, so you can use that, but then you can sit Fargate on top, which I find really interesting. And then Kubernetes, as I've mentioned, you have Azure Container Apps, and then you have the Google one whose name eludes me, but there are many deployment targets for this standard, this virtualization primitive essentially.
The Google one is called Cloud Run.
Cloud Run, that's the one, thank you. Yeah, I was literally researching this over the last couple of days because I've only ever used AWS. Thank you. So then, onto the meat of what I actually wanted to talk about today, so hardware accelerated Docker. So Docker Engine actually supports multiple container runtimes. So by default, when you install Docker, when you run a container, it uses a runtime called runc, which is brought in via containerd, which I think essentially provides like the runtime and other multiple dependencies and like a tool chain as far as I understand. But runc is the default container runtime. But you also have alternative runtimes that you can connect to Docker via configuration that allow containers to target non-typical execution environments. So there's one called wasmtime, so you can build containers for applications that are then actually run in WebAssembly runtime, so that's like the browser or maybe back-end WebAssembly runtimes. And then there are also runtimes that allow us to run containerized workloads on the GPU. Unsurprisingly, otherwise I wouldn't be here talking about this today. So why use hardware accelerated containers? So we have the same isolation and portability benefits as regular containerization technologies. It's quite lightweight. The isolation, it gives us improved security, for example, and that sort of thing essentially. The ability to scale GPU-dependent applications using existing containerization deployments. So if we think Kubernetes, for example, where we're using GPU-enabled nodes, that can allow us to, not trivially, but more easily horizontally scale GPU-dependent applications in a way we may already be familiar with and using an approach that's fairly widely used in the industry. And if we think about machine learning specifically, we might have a real-time model that we serve real-time inference through via HTTP, and we essentially need a means of scaling this horizontally as the demand for inference changes. So we can use those existing approaches, but with hardware-enabled, GPU-enabled hardware, underneath. It can be easier to parallelize hardware accelerated workloads, and that sort of leads on to my next point as well. They're tying together, I suppose. So you can run multiple containers simultaneously. I suppose traditionally with hardware accelerated applications, a GPU probably would balance that parallelization and that time sharing anyway, but you can use the parallelization that containerization technologies provide on top as well, and you can also assign specific graphics cards to individual containers. So say you had a machine with 3 GPUs, you could assign set containers to GPU 0, GPU 1, GPU 2, etc. So it gives you that level of hardware assignment as well, again in a way with which one might already be familiar if one has used containerisation technologies fairly extensively. So a practical, concrete way of hardware accelerated containerisation is the NVIDIA Container Toolkit. So this is a set of technologies for running hardware accelerated containers on the GPU, obviously. It's designed for NVIDIA CUDA applications, which is NVIDIA's solution for, rather than traditional graphics libraries and drivers, it's instead a means of providing APIs and a library for highly parallelized compute applications that can run on NVIDIA GPUs. And you do have emerging now like tensor units and HPC cards, but essentially, to get into the weeds, it's all heavily based on linear algebra and matrix multiplication anyway, which is why GPUs are really well suited to this sort of thing. And it includes a container runtime that executes containers on compatible NVIDIA graphics cards called NVIDIA quite simply. So we mentioned, as we'll see in a bit, we mentioned runc. So NVIDIA is an alternative compliant runtime that's compatible with Docker. And I think there is, I don't know if it's OCI compliant, but I think it does work with Podman too. And there are many Docker images that already integrate with CUDA libraries or the CUDA runtime. So you have an official lower level CUDA image you can derive your own images from. PyTorch, which is a Python machine learning library, provide a CUDA derivative image so you can run your machine learning models on the hardware by packaging them with this existing image. For example, this community effort called Linux Server provide a Blender image, and that also supports CUDA rendering out of the box. And then I'll share my slides at the end, but I've put a few links into useful places as well. So in terms of getting started, running GPU-enabled EC2 instances is probably quite costly, I'd imagine. And I remember once I set up an EKS cluster, a standard one, and that pretty much billed me $100. So I thought, yeah, that's not going to be viable for me in my personal exploration. So at home I do have a desktop PC, but being a Linux user, my graphics card is AMD. Great for Linux because of the open source drivers being very well supported, but not great for machine learning because then AMD, they have dabbled and they do have a technology called ROCm that's essentially like CUDA, but it's very poorly supported, especially on consumer cards. So as an aside, there are two efforts. I think, is it ZCUDA? There's an alternative to NVIDIA and CUDA. It's a CUDA compliant runtime for AMD cards, but it's quite experimental. And there's also OpenCL as well, which might become the more prevalent standard over time. But anyway, I digress. I wanted to keep my main desktop AMD, so I thought, well, I'll just build a little rig with a GeForce card, so I can experiment with CUDA and run a lot of these technologies. So it's not the most high-powered machine in the world. It's only a Ryzen 3 processor, 16 gigs of RAM, so it's probably a bit more entry point. And I opted for an RTX 3060 because it's a fairly capable card but not super high end, and again it was mostly for a proof of concept. It's got 12 gigs of VRAM, so typically if you're working with large geometries and doing rendering jobs or running machine learning models with large data sets, there's going to be gigabytes of data you essentially need to drive into the VRAM. So the more VRAM you can essentially get your hands on, the better generally. And this cost me about 600 quid to build. So installing and configuring the CTK, it's straightforward enough. So you have to, so this is Debian 11, but no, Debian 12. So everything here is essentially, in terms of package management, I'm using the Debian means apt, but You can essentially use any Linux distro. You install the Container Toolkit from your favorite package manager. It provides a CLI that you can use to configure your container platform of choice with. Then you typically need to restart that. And then there's additionally this last statement that I needed for running in user space, which I'll get into. And I'm not fully sure what it does, but it's necessary, so I've just included it. And if I run the docker info command, it gives you a whole host of information, but I've truncated it. And we can see in the server.runtimes property, it has runc, it has v2 of runc, and then it now has this NVIDIA runtime as well. So you can now target this runtime in any docker command you use. And a note as an aside, I mentioned running in user space and running rootlessly. So by default, Docker Engine will be installed to run as the host system's root user. And this is not brilliant for security, because depending on what the vulnerability would be, if there was a particular vulnerability that came to light, having a high level of privilege would perhaps make it more easy to manipulate. So I've always advocated for running Docker in rootless mode, and Docker provides a set of tools for doing that once you've installed the base distribution. And the NVIDIA Container Runtime, fortunately, also supports this mode. It means you have to load the NVIDIA and NVIDIA UVM kernel modules in explicitly at runtime using modprobe, and any devices that are found, any NVIDIA devices found on the host system, need 666 permissions, rock and roll, I know, in order to be accessible within the userland Docker engine. So there's a script to facilitate this. I might as well open the link because it's quite interesting, I suppose. Yeah, so they literally provide you this script and I'm just going to close my display settings because I realise it just says mirrored displays at the top. So it gives you this device no verification script that will do those two steps for you, or it will do the mod probe and set the permissions. So if I go back into my slideshow, so we run that script. And then it will do those bits that I needed, and then you can run these hardware accelerated containers in rootless mode. So actually running a container on the GPU, so I mentioned the Linux server Blender image a while back, literally 3 slides ago, and I don't know why I said that, and we can see you can use the docker run command as we did earlier. You provide a runtime argument, in our case NVIDIA. There's a GPU's flag, and that's explicit to Docker Run, which I think is really cool. Since my hardware only has the one GPU, I just say all, and then you need to nonetheless set this environment variable, and I think that's for CUDA specifically, if memory serves correctly. Then we mount a volume that Blender can use to write the outputs into that binds to the host system, so I can then get those files. And then I'm using a project, so Blender hosts open movies, and there's a Blender Studio website where you can access the assets. So some are free, but some are behind an €11 monthly subscription, or it was when I was briefly subscribed. And you can download the various scenes and the geometries, etc. So then the subsequent pieces here, I'm running Blender, and then I'm passing the project, any configuration, and then there's a specific set of arguments for Blender. So the backend, so we use the cycles renderer, and we use the cycles renderer because it's compatible with CUDA, and I specified D in Docker Run to run that in detached mode. So we get the hash of the container. And then if I run Docker PS, we can see it's running. I can run Docker logs on the container, and it will give me any standard out and standard error output, and Blender's CLI will show us we're running the frame. And then we can verify it's running. So as part of the NVIDIA drivers, you have a tool called NVIDIA SMI, and that will show you the state of the detected graphics cards, temperature, power consumption, and any processes. So this process name Blender and the GPU memory usage, that's a result of running Blender within the container. And then what we end up with is something like this. So my rendering doesn't look as pretty, but I left it overnight and it actually worked. So it took me I think it probably needs denoising a little bit realistically, but this took 9 hours to render 17 seconds of video essentially. And then if you're familiar with Docker Compose, which is essentially a developer experience tool on top of Docker that allows you to specify configurations to run multiple containers together on a shared network and with shared resources, you can also run Docker Compose on the GPU. So this is a web UI for stable diffusion that is essentially a Docker Compose config. And we can see here so this is just a reusable property that further on in the config gets brought into Docker Compose services. For the deploy property of the service, you can specify device reservations and you can specify what driver to use, the capabilities and the device ID of the GPU in this case you want to pass forward. And then you run Docker Compose in the usual way. This profile argument, it's just something specific to this one Docker Compose config and how they've set it up. But generally, you can use Docker Compose in the same way. And again, it will run it on the GPU. And if we've got time, I've actually port forwarded my instance of verified earlier. And it is running and it's got a stable diffusion. So if there's time, we can have a bit of a poke. And I tested it and I put Fred Dibner eating a sandwich. I thought it would be pertinent to, Lancashire. And because it's an older model, I don't think it really knew who he was, but it tried. So deploying to production, we've already touched upon this a bit admittedly, so I'll keep it brief. So we could run on an OCI execution engine running on a GPU-enabled machine, so self-hosted as I've done. EC2, G2 and G3 instances, Azure N-Series virtual machines, GCP, compute engine instances with GPUs. These are all managed options. And then, or managed at the hardware level, but you're still at a lower level deploying the software onto it. But you do have managed container deployment services as well. So ECS has support for GPU EC2 nodes internally, so ECS will make use of the G2 and G3 instances as the underlying nodes. And then there are GPU profiles for Azure Container Apps, which are currently in preview. And then there's Kubernetes as well, so Amazon EKS, Azure Kubernetes Service, GKE, these all currently support GPU-enabled nodes. So if you have familiarity with Kubernetes and you want to use a managed service, then you can make use of GPU nodes. And on the subject of Kubernetes, I did want to dig a bit more deeply, but essentially, as I've already mentioned, it's a containerisation runtime that runs OCI containers in a cluster using any particular topology. You could be using a managed service, you could be using your own physical nodes, that could be like multi-region, global, and again this supports hardware acceleration. So there's the GPU operator as part of the Container Toolkit that NVIDIA provides that sits on top of Kubernetes. So again, you have this first-class integration for running CUDA dependent containerised applications on Kubernetes as if it were a standard application using Containerd, or which whatever the default Kubernetes runtime is. And what I want to do next, so I'm working with Al quite closely on this. Al's a good friend of mine, and Kubernetes is more his bread and butter really, so we're going to look into this together. So there's a Kubernetes implementation called Minikube. Typically use it for local development. It's a self-contained Kubernetes cluster in software. You can install onto your own machine, you can deploy deployments and services and create nodes against it as if it were a real Kubernetes cluster. So really it's more for local development, self-learning. And that also does support the NVIDIA GPU runtime. I think it currently only supports Linux, but essentially the support is there nonetheless. And one more thing I wanted to touch upon, which I think I've mentioned briefly, is just how critical this is in MLOps. You have Python models that are real-time. You might be providing customer recommendations, for example, and the demand can vary based on times of the day, particular times of the year, and even it could be entirely seasonal, different customer promotions going out. Being able to scale machine learning models horizontally in a hardware accelerated way is critical. And I'm not saying containerizing everything and putting it on a containerisation clustering runtime like Kubernetes is the only way. There are non-containerised alternatives, but there's a lot of familiarity with Kubernetes. I think it's a pragmatic choice because you get those container isolation benefits and those existing practices, but then you can scale elastically and do so using hardware acceleration underneath for the inference. So in today's world of machine learning in particular, it's really beneficial and ties in very nicely. So yeah, thank you for listening. I'm happy to answer any questions, and if anyone has a bit of time, I might briefly get Stable Diffusion up and I can show you the practicalities of, like SSH into the machine, running NVIDIA SMI, etc.
Sounds great.
I was going to ask a question about it.
Yeah, sure.
What exactly is the NVIDIA runtime doing?
So
the reason I ask is because, basically Docker is a coordination of C groups and a few other things.
Yeah.
So you were running on the kernel, you're a process with a bunch of guardrails put on you. And so the NVIDIA runtime, the only thing I can imagine is that it's opening up some C groups to allow access to NVIDIA hardware.
Yeah, I think there's a really good diagram somewhere.
So it's almost like an extra configuration.
Yeah.
Not really a runtime as I would think about a runtime.
Yeah, fair.
I think, is it this page on the overview? Yeah, so here's like a really good representation of it. So the CUDA toolkit has to sit within the container. So I mentioned the CUDA base images. So that will contain the CUDA toolkit, I'd imagine. And then that runtime, it integrates with the CUDA driver. So I assume it's that driver essentially redirecting it to the physical hardware, at least as far as my knowledge goes anyway. So there's probably a million bits of nuance to it at a more deeper level, but that goes well outside of my knowledge essentially.
So there's a CUDA driver in that you had to. Oh, that was the thing that you said you had to mod probe in.
Yeah, exactly.
Okay.
Yeah.
So it's providing access to that. Okay.
Nice. Yeah, I'll show you one more thing really quickly then. So I've SSH'd into. So last night I exposed the SSH and a particular HTTP port on my router. For some reason my SSH keys aren't working. I don't know why it's asking for my password, but I'm in the box now. And if I run docker ps, we can see there's a container running, and this web UI Docker 01, it's from that Stable Diffusion Docker Compose config I mentioned, and we can see it exposes this port 7860 that I then bind to the host. So now if I grab this IP And what I'll do as well while I'm here, I'll run NVIDIA SMI, and you can pass it an L argument that will just keep rerunning the command. So we can see Python's running. I assume that's the inference server and then the underlying model as well. I'll just bring this to one side for a moment. And then I'll bring this to the other side. If I grab that IP and then I think I forwarded it to 17860, we get the stable diffusion run UI. So this is running on the box directly. So does someone want to give me some sort of a prompt to run?
Couldn't possibly.
What I'll do maybe is I'll type something like a tech meetup engaged in a lively discussion.
We're all going to get really insulted.
That wasn't supposed to sound passive aggressive, so I do apologise. Right, okay, so I'll generate 2 batches. No, I'll generate 3 batches with a size of 4 images per batch. I have actually had this run out of memory on me before, so that might happen. I'll run generate. And what we should see eventually is as this reloops, do you see how the memory usage just jumps up to 2 gigabits essentially.
It's not bad, that is it?
So there's an upscaler as well. Now I don't know if I've actually provided the upscaler here, unfortunately, so they might be quite low quality. But yeah, you can, the refiner, I think. There's one applied, but I think, it's not necessarily gonna, let's have a look. So again, this is quite an older model, so it's not like stable diffusion quality as we know it today. But essentially, this is generated on a consumer grade CPU in a container running through the NVIDIA container runtime, essentially.